Let's now look at all the corollaries of Lagrange's theorem in the book. These are important in their own right. Lagrange's theorem is a big theorem. You could call it the fundamental theorem of finite group theory, the most important theorem about finite groups, the foundational theorem that you can use to do so much. These corollaries immediately follow from Lagrange's theorem. First corollary says if G is a finite group and H is a subgroup of G, then what in the world is that? I haven't mentioned that in class yet. What's that symbol mean? Did you do the reading? You remember what that's called? It's got a name. It starts with an I. I-N. I-N-D. Don't remember from the reading. I-N-D-E-X. What did I just spell? Index. It's called the index of H and G. What's its definition of this symbol? It's right above it. The index of a subgroup H and G is the number of distinct left cosets of H and G. So you've got a group G. Okay, let's make a little diagram. Could be finite. It even could be infinite. I mean, mostly we're thinking about finite groups here. G could be an infinite group. You got some subgroup H of G. I also want to draw cosets of H and G. There's one coset, AH. Here's another coset, BH. Here's another coset, CH. DH. And EH. I probably shouldn't use the letter E. FH. Right, because E stands for the identity. Actually, H does equal EH, where E is the identity, because H is a subgroup. The left coset of H and G containing E does in fact contain E, and it does equal H itself. How many left cosets did I draw? 6 of them in this picture. If this were really the case, that would mean the index of the subgroup in G with this funny notation is 6. There are 6 distinct left cosets. They do form a partition of G. The intersection of any 2 distinct left cosets is empty, and their union is all of G. In fact, you can define an equivalence relation using cosets. So that's what the index is. And this is saying, as a corollary of Lagrange's theorem, that index, the number of left cosets of H and G, is the order of G divided by the order of H. Why? It's in the proof. So if you want to count the number of left cosets of H and G, compute this ratio. For example, just to take a quick numerical example, if G had order, say, 50, and H has order 5, then the number of left cosets would be 50 divided by 5, 10. Right? It makes some intuitive sense. If each coset has 5 elements, and by the way, the cosets would have the same number of elements. That's part of the proof too of Lagrange's theorem. And there are 10 of them, you got 50 elements total, the entire group. So it's actually pretty intuitive when you think about examples. Next corollary. In a finite group, the order of each element of the group divides the order of the group. That could be an exam problem. Prove that. You want to use Lagrange's theorem. Let's just think about it without looking. You got a finite group G, some order N. You got an element of the group. You need to show the order of the element divides the order of the group. Wait a minute. What's the order of an element? It's the smallest positive power that brings you back to the identity, right? How can I use that to show that number, that power divides N? Use the fact that we know, this is from the past, that the cyclic subgroup generated by the element is going to have an order, a number of elements equal to that lowest power that brings you back to E. And that's what the proof essentially is. Recall that the order of an element is the order of the subgroup generated by that element. And therefore, by Lagrange's theorem, that order has to divide the order of the group. Next corollary is exactly what we did a few minutes ago. every group of prime order is isomorphic to ZP. Okay, we phrased this differently. Problem we just did was that if G has prime order P, then G itself is cyclic. But here they're saying it's isomorphic to ZP. Isomorphism. What's the difference? Suppose G has prime order and A is in G, but not equal to the identity. This looks like our proof. Then the order of the cyclic subgroup generated by A divides P, and it's not equal to 1. Therefore, the orders are the same. And we said that means G is the same as the cyclic subgroup generated by A. But they're saying the corollary that it's isomorphic to ZP follows from an example in chapter 6. What was that example? That example was showing any cyclic group of order n, where n was not necessarily prime, is isomorphic to Zn. We came up with an isomorphism. I did mention this in class. You got a group that's cyclic. That means that group is isomorphic to Zn for some n, whatever the order of G is. To prove that, technically, you have to come up with an isomorphism. A phi from G to Zn that's one-to-one onto an operation preserving. And one thing you can do, one example of an isomorphism is to map A to 1 and to map any power of A. Well, maybe I should use a different letter here. The mth power of A gets mapped to M. Essentially mod n. If M is bigger than n, I'd have to mod by n. That ends up being an isomorphism. We're not going to prove that, but that's what it is. Effectively, we're mapping a generator of G to a generator of Zn and sort of extending that, hoping that that works, though you'd have to prove it. The next corollary says, let G be a finite group and let A be an element of G, then A raised to the order of G power equals E. Kind of a weird little property, but true, and sometimes useful. They use a previous corollary that the order of A divides the order of G, this one here, to say that, okay, that means the order of G is the order of A times some integer K. And now do this calculation using effectively a property of exponents there. They skipped a step. You could also write that this equals that. That would be a property of exponents that you could put in between these two equal signs. This would then be e to the k. All these corollaries are examples of things that could show up on the exam. Although probably not corollary 5, Fermat's little theorem. Don't say Fermat, say Fermat. Fermat's little theorem. For every integer a and every prime p, a to the p power mod p equals a mod p. Proof's not too hard, but it's kind of tricky enough that I wouldn't necessarily put it on the exam. Is this something you should know? It's a naming theorem. I don't typically test on Fermat's little theorem, but I am emphasizing it right now because it's historically an important little theorem. In fact, it's a big theorem in terms of its applications. Fermat's little theorem makes your internet transactions safer. It's the basis for a lot of things in modern cryptography. The truth of Fermat's little theorem. Especially when A and P are big numbers. This helps to make secret keys that keep your internet transactions secure. I'm not going to go into detail, but historically it's important, and it also is important for applications. It's got a name, must be important. I don't typically test on it, but